In this video, we're going to continue exploring the behavior of nonlinear amplifiers. And we're going to do so by looking at the cubic term in our equation, which is referred to as the third-order distortion term. Like before, we're going to derive a trig identity that we've all probably forgotten about by making a polynomial out of Euler's formula. It's worth noting that I calculate the coefficients for this polynomial using Pascal's triangle. So a cubic polynomial has coefficients of 1, 3, 3, and 1. And I find that's just kind of a quick way to do these derivations. The result of this process is on the right. Cosine cubed of x is equal to 1/4 of cosine 3x plus 3 cosine x. Also, just like before, we can substitute that identity into our V out equation. Just like second-order distortion, third-order distortion has some interesting properties. First, we see that the third-order term produces a harmonic at 3 omega. Like before, we can define an HD3 measure, which is the voltage amplitude of the third harmonic divided by that of the fundamental. The ratio of the coefficients of those terms comes out to 1/4 A3 over A1 times VZP squared. One interesting note is that HD2 grew linearly with VZP, while HD3 grows as VZP squared, which shows that higher harmonics become more significant as you provide more and more input power. It's also useful at this point to define a measure called total harmonic distortion, or THD, which measures how distorted a sine wave is as if it passes through a linear system. THD is the sum of the power in the harmonics divided by the power in the fundamental. And we can actually compute it in a pretty convenient way, because each of our harmonic distortions is the voltage in a harmonic over the voltage of the fundamental. So THD is equal to the sum of our HDX terms squared, square rooted. The other term in our third-order distortion expression is 3 cos omega t, which falls directly on top of our input, because it has the same frequency as our input signal. It's got omega inside of the cosine. Because A3 is often negative, this term has the effect of reducing the gain of our system, which is a way of indicating that the compressive behavior of the amplifier has started. This is showing the third-order harmonic pulling us away from a straight linear gain. Accordingly, this effect is called gain compression. We can describe gain compression mathematically by gathering terms that are multiplied by cosine omega t to define the effective gain, and then dividing all of that through by A1 to find the ratio of effective gain to linear gain. This ratio of effective gain to linear gain is useful for defining an easy-to-measure parameter called P-1 dB. P-1 dB is the input power that causes our gain to be compressed by 1 dB. We find it by taking 20 log of our effective gain, using 20 as our coefficient instead of 10 because we're measuring power instead of voltage, and setting that equal to -1. We can also flip the equation around to find the value of VZP that would cause us to reach P-1 dB. Finally, here's a plot showing the frequency content that we've introduced so far. A signal passing through our nonlinear amplifier will have a second and a third harmonic. It will have a slightly compressed gain, and it will have additional power at DC, causing a small DC offset. So in summary, the third-order distortion term creates gain compression and a harmonic at 3 omega. The third-order harmonic is described by the HD3 measure, which appears on this slide. The effect of all of the harmonics combined is given by total harmonic distortion, and we can find that from the HD2 and HD3 and HD4 measures by squaring them and adding them in quadrature. And finally, gain compression is measured by a power value called P-1 dP, and we found the voltage at the input that you need to apply in order to reach P-1 dB.